Okay, so we've looked at how capacitors can charge. Next we want to look at how they can discharge. Okay, so we have a capacitor here, which they've drawn to look almost like a battery because it's going to, in a certain sense, be providing the function of a battery. It's causing the flow of current because we have a capacitor that is initially fully charged and there's a potential difference V naught above it. Now, how did it get charged? We hooked it up to a battery, but now we've removed the battery, and so the capacitor is going to send charges, and charges are going to flow through the circuit when the switch is connected, and the current will flow through the resistor as the charges redistribute themselves. Now, there's a couple of different ways that you can look at this. You can consider this in terms of the Kirchhoff loop rule again. We can say that the sum of the voltages is going to be the voltage across the capacitor, which is acting like the battery now, so it's positive, and then as the current flows through the resistor, it's going to have a minus IR voltage drop across it. And so the sum of those voltages is equal to 0. And it doesn't really matter. You could call the voltage of the battery negative and the current times resistance positive. But you know that they can't have the same sign because they have to add up to 0. That's just the way it is. Another way that we can think about it, though, is we could actually start here and think about what's the voltage at that point and that point. It's got to be the voltage drop across the resistor, IR, but it also has to be the voltage across the capacitor, which is going to be Q divided by C. And so we can simply equate these directly, or we can use the Kirchhoff loop rule and bring the IR over here. We get the same result. IR equals Q over C. Now, just like we did before, we're going to plug in the definition of the current, which is minus dq over dt. Why is it minus? Because basically because the current is changing in the negative way. It's decreasing. And so the capacitor is discharging, so there's less and less current going. So we have, this is our starting point, and we again will apply the separation of variables, so we get all the terms with Q on one side and all the terms that are not Q on the other side. And so doing a little bit of algebra, we end up with dq over Q is equal to minus dt over RC. Now at this point we can simply integrate both sides, and the integral on the left will go from some initial charge Q naught to some Q, and then the time, of course, will go from some time equal to 0 to some time equal t. And of course the integral on the right hand side is easy. The constant values RC just come out of the integral, the minus sign comes out of the integral, and the integral of dt is just simply t. And the left side integral is simply the natural log. dq over q gives us the natural log. So if we plug in the limits of our integral into our integrand, we get the log of q minus the log of q naught is equal to minus t over RC. Again, we can use the property of logarithms to combine the difference into a fraction, and we get the log of q divided by q naught is equal to minus t over RC. And of course, we were trying to solve for q, which is the charge on the capacitor as a function of time. So in order to get q by itself, we need to get rid of that logarithm. And so to get rid of the natural log, you simply take the exponential of both sides, and you'll end up with q over q naught equals e to the minus t over RC. So we get q over q naught is equal to e to the minus t over RC. Then to solve for q, we just bring the q naught over, and our final expression that we get is q is equal to q naught e to the minus t over RC. And so we see the charge acting on the capacitor is an exponential decay. The minus sign shows us that it is decaying exponentially, and that's the form of the curve that we get for the charge on a discharging capacitor as a function of time. Notice again, we still get this RC value here, which is the time constant of the circuit. That's very important in RC circuits. That value is the time constant of that circuit, and it tells you basically how quickly the circuit is going to decay. And of course, for a charging circuit, it tells you how quickly it's going to charge. If we plot this function, Q is Q naught e to the minus t over RC, we get an exponential decay. And if we plot it in terms of the number of time constants that have gone by, one time constant, two time constants, three time constants, remember the units of time constants are going to be seconds. So you're going to calculate a time constant, 50 milliseconds or whatever it is. And so this would be 50 milliseconds, 100 milliseconds, 150 milliseconds. Whatever the time constant of the circuit is, you're going to get this exponential decay. And remember that when you have this exponential decay, when you get to one time constant, you've basically fallen to 37% of the initial value. And once you get beyond about 3 time constants, you've pretty much, asymptotically gotten pretty close to 0. Now this expression for Q, that is of course, again, that's the charge on the capacitor as a function of time. We know from the fundamental capacitor equation that the voltage is related to the charge and the capacitance by Q over C. So if I simply divide this expression that I've got a box around by C, that'll give me V sub C, which is the voltage across the capacitor at any time t. So this up above is the charge on the capacitor as a function of time, and this expression down below is the voltage across the plates of the capacitor as a function of time. In other words, I plug in a time value for t, that will tell me what the voltage across the plates is at that time. And of course, to calculate the current, we simply take the derivative of Q, that's this expression up here, hit that derivative of that with respect to t, and when you do that, you get this expression here. And remember, our value for current was negative because our charge was decreasing on the capacitor. And so when you take the derivative, you get this minus sign coming out from the chain rule. You get this 1 over RC coming out from the chain rule. And that leaves us with this expression, Q naught over RC times e to the minus t over RC. This Q naught over RC, that's obviously going to be some kind of current. And so typically, we would write this expression as I equals to I naught e to the minus t over RC. Now what's interesting is that in the discharging case, all three expressions, charge, voltage, and current, give you an exponentially decreasing function. So we can summarize these formulas. I have them just listed here just for your convenience. But these are the expressions, again, when you have charging, this is the charge, the voltage, and the current. And for discharging, you have the same for each of these. And that's how we can deal with both charging and discharging capacitors.